Hello, you're welcome back. Okay, so we are going to be discussing quantity of heat energy. All right, so quantity of heat energy. Now, before we look at the measurement of the quantity of heat energy in a body, first, what's heat energy? Okay, previously we actually talked about temperature, and we said that temperature is a physical quantity that actually measures or indicates the rate of flow, okay, of and the direction of flow of heat energy. So that simply means that I can define heat energy, okay, as a type of energy that actually transfer from, that flows from a hot object, okay. It flows from a hot body to a cold body. So anytime there's a difference in temperature between a hot body and a cold body, there's going to be energy that always flow from hot to cold. The direction is always from hot to cold. Such energy is heat energy, okay. So now everybody everybody, okay, can have a particular content of heat energy, and the content of heat energy also depend if that body is actually losing the heat. Why? Because a hot body loses heat, a cold body gains it. All right, because if you actually bring hot or body to that, okay, in contact with a cold body, what you should expect is heat flowing from the hot body to the cold body, okay. So now where quantity of heat is actually the quantity, okay, or the measure of the amount of heat that either a cold body can absorb, all right, or the hot body can actually lose. So that is quantity of heat energy. So the quantity of heat energy on a body is actually defined as either the quantity of heat energy that body can absorb or that body can actually lose to another body, okay. So now I use Q to represent the quantity of heat energy. Now it should be noted that the quantity of heat energy a body can evolve or absorb is directly proportional to the mass of that body, and of course to the change in temperature of the body, delta theta. All right. So now you know very well that if I should introduce an equal to, all right, if I should change the proportional side to an equal to, I'll have to introduce a constant. Now this time around, the constant I'm introducing is not going to be K. The constant will be C. So I'm going to have Q is equal to MC delta theta. Okay. So the quantity of heat energy of a body is actually measured with this particular formula. MC, change in temperature. So let's look at, of course, the parameters. The Q is the quantity of heat energy. Okay. Quantity of heat. And of course, you know very well that it is measured in joule because it's an energy, okay. Heat is measured in joule. All right, then the M is the mass of the body. Then of course delta theta is actually the change in temperature or the rise in temperature, okay. So let me just call it change in temperature because it's either the temperature is actually decreasing or it's increasing, so it may not necessarily be rise, okay. In some cases it's decreasing, in some cases it's increasing, so I just call it change in temperature. All right, so now this constant I've introduced now, that constant is, okay, is what I'm going to explain. It's a constant, okay, called, known as the specific heat capacity. Specific heat capacity of the substance. Specific heat capacity. So which simply means that, okay, it's a constant that depends on that particular substance or the material of, okay, that material that is used in making up, that makes up that substance. All right, now every substance have its own specific heat capacity. Every substance have its own specific heat capacity. How can I define specific heat capacity, and what is the importance or the implication of specific heat capacity based, okay, on the quantity of heat energy of a body? Okay, now let's actually, before I define it, let me make it the subject of formula from here. So the specific capacity, if I should make it the subject, is going to be equal to Q, then divided by M delta theta. So now let me now define it. The specific heat capacity of a substance is defined as the quantity of heat energy that is required to change 1 kilogram of that substance by 1 Kelvin. I'll go again. The specific capacity of a substance is the quantity of heat energy that is required to actually raise the temperature of 1 kilogram of the substance by 1 Kelvin. All right. So the mass of the substance is specific. That is what they call it, specific heat capacity. What is the implication now, and what's the advantage? Okay. We discovered that there are some substances that require much heat energy before their temperature actually rises to a noticeable amount. That is why we have, okay, based on heat a substance can absorb, we can say we have substances known as conductors. Okay, conductors of heat and insulators. So if I should actually differentiate conductors and insulators based on specific capacity, I would say that a conductor are those substances that have low specific heat capacity. Low specific heat. Why? All right. Why do they have low specific heat? Why? Because you just need the quantity of heat energy that is required to raise the temperature of a conductor is very small. Okay, so a conductor, once a small temperature is supplied to a small heat energy supplied to a conductor, then you discover that conductor actually the temperature rises noticeably. Okay, compared to insulator that actually requires, so insulator have high specific capacity, high SHC. Why? Because it will take more heat energy for you to be able to raise the temperature of insulators, okay, to a noticeable amount, okay, to let's say by 1 Kelvin. All right, it will need to take. So that means if you apply heat on insulators, you discover that, you understand, you apply a very high quantity of heat, you will not actually notice any rise in temperature, especially when, let's say, you are heating up something like wood. Okay, so compare when you heat wood to when you heat metals. All right, so that means low specific heat capacity is an attribute of conductors, while high specific heat capacity is the attribute of insulators. All right, now specific heat capacity is actually a constant that should actually be gotten. Every substance have their specific capacity. For example, I know very well that the specific capacity HC of water, I can still remember this one, okay, is 4,200. Okay, so what's the SI unit? Let's get the SI unit from this derived unit. The SI unit of quantity of heat is joule. SI unit of mass is kilogram, while the SI unit of temperature is Kelvin. Okay, so that means the SI unit of specific heat capacity is giving us joule per kilogram, then per Kelvin. So every substance have its own specific heat. Okay, have an individual substance. Okay, and of course there's a table that lists out different substances and their specific heat capacity. And of course, in this particular video, we're going to look at how you can determine the specific heat capacity of a substance if you are being given such a substance to determine its SHC in the laboratory. Okay, there's another type of heat capacity which I want to introduce. Okay, there's another type. Okay, or will I call it another type? There's what is known as heat capacity. This one is not specific, right? The other one is called specific capacity, but this one is just heat capacity. What's the difference between this and the other one? Okay, now heat capacity is simply defined as the quantity of heat energy that is required to raise the mass of a body by 1 Kelvin. What's the difference? Okay, what difference is this definition? What's the difference of this particular definition? Okay, different between this definition and what I actually gave before. Remember, for specific heat capacity, the mass is specified, which of course we define it as the quantity of heat energy that's required to raise the temperature of 1 kilogram. That means the mass is specified. But in heat capacity, okay, the mass is not specified. That's why we define heat capacity as the quantity of heat energy required to raise the the temperature of a body, okay, by 1 Kelvin. All right, now, what is the relationship between specific heat capacity and heat capacity? All right, so of course, I'm going to use H to represent heat capacity. Heat capacity of a body is equal to the mass of that body multiplied by its specific heat capacity. So that's the formula. Okay, so if you multiply mass of the body by its specific heat capacity, you've actually converted it to heat capacity. Let's look at the SI unit. Of course, the SI unit of mass is kg, right? And we know that the SI unit of C, specific heat capacity, is joule per kilogram, then per Kelvin. Okay, so in this case, Kelvin cancels Kelvin. So the SI unit of heat capacity is just simply joule per Kelvin. So there's no mass. To show you that mass is not specified, okay? Joule per Kelvin. So please take note of this. It's very important. All right, as we now look at the determination, okay? Let's talk about the determination of specific heat capacity. But before we talk about the determination of specific heat capacity, should I just let me illustrate this formula, okay? The formula for quantity of heat energy. Let's say a situation where you are being asked to evaluate the quantity of heat energy on a body of mass 1 kg. If the temperature of that body, okay, actually rises from theta 1 being 10 degrees Celsius to theta 2, okay, 20 degrees Celsius. Let's say that particular the specific capacity of that body is the substance is water. Okay, let me just 4,200 per joule per kilogram per degree Celsius. Okay, so simple. Q, the formula is mc delta theta. Of course, you know change in temperature is always final temperature minus initial temperature. So it's gonna be mc, then theta 2, final temperature minus initial temperature theta 1. Okay, though there are some cases I will do theta 1 minus theta 2 depending on the temperature that is bigger. Okay, in this case, in this case, the final temperature is greater than the initial temperature, so that's why I'm doing theta 2 minus theta 1. If it is the other way around, then I would have done theta 1 minus theta 2. Okay, all right. So now this is going to be equal to 1 times 4,200, then temperature 20 minus 10. So that's going to be equal to 4,200 times 10. So that should be 42,000 joule. 42,000 joule. Okay, so that's the application. Now let's look at let's look at the determination of specific capacity of a substance. SHC. Let's say you are being given a substance. You don't know what that substance is. Okay, I say, okay, go to the laboratory, determine the specific heat capacity of that substance. What method are you going to employ? All right. Now, the methods that we are going to use in the determination of specific heat capacity, okay, is just two methods. One method is a method known as mixture. It's mixture method. Now, the second method is electrical method. All right, so I'm starting with the very first mixture method. Okay, of course, as the name implies, mixture. That means I am actually mixing I'm mixing two substances together. All right, how do we apply mixture method? What's the procedure? Now, before I actually get to the procedure, okay, any of this method actually employs any of this method of measurement. Remember, what you're measuring is C, okay? From the formula of C, we know that C is equal to Q divided by M delta theta. So it simply means that if I want to measure C, that means I need to supply that substance I want to measure EC with heat energy. I need to measure the mass of that substance and also need to measure the change in temperature. Are you okay? So now the method we employ is actually basically based on how this Q, this heat is actually being supplied. Okay. So it's basically based on, so the method, okay, to the method I employ to thus the supply of this heat, okay, in this formula, we actually determine the which of this method I'm actually describing. So in mixture method, okay, in mixture method, the only way I supply heat to that substance is to bring that substance in contact with a hot object. All right. So that means I will have a hot object which I know its specific heat capacity. I heat that object. All right. Then I now bring that object in contact, all right, with the cold object. Of course, the cold object is the object that I want to measure the specific heat capacity code. Of course, you know the principle. You know very well that heat will always transfer from the hot object to the cold object. That transfer of heat will continue until the temperature of both the hot object and the cold object is equal, okay? So that means all the heat from the hot object will be transferred to the cold object. So the principle that we employ in mixture method is a principle known as heat lost. Heat lost by the hot object is equal to heat gained by the cold object. Okay? So if you know how to apply this principle, you can solve question, okay, based on mixture method. All right, so now let's work on that. Of course, the object that is losing heat is the hot object. So I will simply say that, of course, heat is giving us MC change in temperature. So I'll say MC change in temperature of the hot object is going to be equal to the MC change in temperature of cold object. Now, there are some things you should know. For hot object, the change in temperature of the hot object is always decreasing. Okay, change in temperature of the hot object is decreasing. It's decreasing. You know that already. So because the change in temperature of the hot object is decreasing, okay, I will always subtract the final temperature, the final temperature, right? No, it's decreasing. I will subtract the initial temperature because the initial temperature is greater than the final temperature. So I will subtract the initial temperature. Okay, let's say the final temperature of the entire system, all right, of the mixture after their temperature come together is theta 3. So I will always subtract the final temperature, the initial temperature of the hot object, okay, from the final temperature. It's always going to be theta 1 minus theta 2. Then for this object that is actually the temperature is increasing, okay, then you know very well that it's going to be the final temperature theta 3 minus theta 1. All right, don't worry, I will actually apply this. So the switch simply means that in this case now I can write the formula MC, okay, let's say the object that is hot, the mass of the object that is the hot object, okay, remember I'm looking for the specific capacity of the cold object. So let me call the mass of the hot object M1, its specific capacity C1, then of course the temperature change theta 1 minus the temperature of the mixture, which of course the final temperature theta 3. Remember the final temperature of the mixture will be the same, okay? Then of course for this object, the cold object M2, C2, then the temperature change theta 3 minus theta 1. That way now I can get this, okay? So that means C2, the specific heat capacity of the cold object that I'm actually looking for, C2 is going to be equal to M1 C1 bracket open theta 1 minus theta 3, okay, then divided by M2 C2. Okay, please, I'm looking for C2, so C2 is not supposed to be here again. Okay, all right, so M2 then multiply by theta 3 minus theta 1 minus theta 3, please pardon me, theta 1 minus theta 3, theta 3 minus theta 1, theta 3 minus theta 1. Okay, so that is how it works. That is how it works. Okay, I think for this to actually make sense out, let's look at some question. Let's work on some question. Okay, let's say you are being given such a question where you have let's say water of mass. Okay, water of mass is of mass 2 kg, and of course this water is at initial temperature of, let's say, room temperature 4 degrees Celsius. Okay, it's now being transferred into another water M2 of mass, let's say 1 kg, then of a higher temperature. Okay, of a higher temperature, theta 2. Okay, let's say theta 2 10 degrees Celsius in a container. Okay, in a container of negligible heat capacity. So if the container is of negligible heat capacity, simply means that the heat transfer is only between the hot water and the cold water. Okay, it's between the hot water and cold water. The container is not getting heat. All right, so now the question is so what's the first? Find the final temperature theta 3 of the mixture. All right, so if you are being given such question, solution is simple. We apply our principle of mixture, which of course is heat lost is equal to heat gain. Okay, so that's going to be the one that is actually losing the heat is M2. M2, of course, C2, then the temperature change. Remember, the one that's losing the heat, the initial temperature will be greater than the final temperature. So I'm going to do initial temperature minus the final temperature equal to the water that's getting the heat, which is M1, multiply by, okay, so I can't, since water is, it is still, I'm dealing with water, okay, two water, they have the same specific capacity, so I'm going to use C, the specific capacity of water here too, the same specific capacity C, then of course the change in temperature. Now for the one that's getting the heat, the final temperature of the one that's getting the heat is greater than the initial temperature, so in this case I'm doing theta 3, okay, theta 3. What am I? Where am I? Okay, I'm M2C. All right, that is the hot object. Okay, so I said that the initial temperature of the hot is greater than the final, so I'm doing theta 2 minus theta 3. All right, so let's go to the code M1C, and that's also said that the final temperature of the code is greater than the initial temperature, so I'm doing this time around theta 3 minus the initial temperature of the code, which of course is theta 1. All right, so let's put our values. As you can see, it's water having the same C heat capacity both sides of the equation, so it is easy for me to just cancel out the heat capacity. So I put my values. M2 is 1 kg. All right, multiply by the change in temperature. I'm having 10 minus the initial temperature, which of course is 4. Okay, is equal to M1. What's M1? 2. The change in temperature theta 3. Oh, please pardon me. I'm looking for theta 3. Pardon me. That's going to be 10. Theta 2 is 10 minus theta 3. Theta 3 is unknown. the final temperature. Okay, so I'm having the same theta 3 minus theta 1. What's theta 1 for? Okay, so let's evaluate this. Open this bracket. 1 minus 10. 1 multiplied by 10 is 10. 1 multiplied by theta 3 is theta 3. Is theta 3. Alright, 2 multiplied by theta 3, I have 2 theta 3. 2 multiplied by minus 4, I have minus 8. Rearranging this equation, so I'm going to have 10 minus 8 comes over, it becomes plus 8. Here I'm having 2 theta 3. 2 theta 3. Of course, minus 1 theta 3 goes over, becomes plus 1 theta 3. Adding this up, I'm going to have 3 theta 3, right? 3 theta 3 is equal to 18. So that way now for me to get my theta 3. That way now for me to get my theta 3, I'm gonna have 18 all over 3. And 18 all over 3 should give me 6. So that's 6 degrees Celsius. If I'm not mistaken, 18 all over 3 is 6, right? Yeah, 6 degrees Celsius. So that is how you apply mixture method. All right, we'll still solve more questions in the next video, but let's now go to electrical method. Let's work on electrical method. Okay, electrical method. Now in electrical method, how do we supply the heat? Okay, the heat is supplied by, in electrical method, by an electrical heater. The heat is being supplied by an electrical heater. So that means the heat is actually electrical heat energy. So the principle of electrical method is simply, okay, electrical heat energy, E, is what is actually supplied to that particular substance that raises the temperature, MC delta theta. Electrical heat energy is equal to MC change in temperature. Okay, now in electricity, electrical heat energy is given as electrical power multiplied by time. So PT is equal to MC change in temperature. This is one way of, okay, expressing the formula in electrical method. Okay, power times time is equal to MC change in temperature. Already, if you have treated electricity, you know that power is always given as current multiplied by voltage. So if I should substitute that into this formula, I will now have power is going to be IV. Okay, then of course I have to multiply by T is equal to MC delta theta. This is formula number 2. Okay, you can use this, or you can also use this applying Ohm's law. You know, from Ohm's law we know that V is equal to IR. Okay, so if I should apply Ohm's law here, if I should replace V by IR, I'm going to have I times I multiplied by RT. Okay, I times I is I square. So the formula can also be expressed as I square then RT still equal to, that's what is used in raising the temperature of that body, MC change in temperature. We can also go again. Another way of expressing this from Ohm's law, we know that if I make current the subject of formula, current is voltage all over resistance. So if I should replace current by voltage all over resistance, I'm going to have voltage times voltage, which is V square. V square then multiplied by T all over resistance. So the formula can also be expressed as V square T then all over R, which is also equal to MC change in temperature. Why am I giving all this formula? Okay, so in electrical method, depending on what is given, you can use either of these. So if the question is, what is given in the question is power and the time, then you use this. If the question is, okay, if what is given in the question is current, voltage, and time, you use this. If what is given in the question is current, resistance, and time, you use this. If what is given in the question is voltage, time, and resistance, you use this. Okay, so we are going to apply this formula in the next video. All right, see you in the next video. Thank you very much.